So welcome back after the break. Hope everybody is around. Maybe you can give me a thumbs up that you're around. At least one. Anyway, let's continue. Next part is supervised segmentation. So until now we have used relatively unguided approaches, the histogram and clustering. They took whatever data they got and did that to the data and found the segments based on that on the data. And the next step is to use the supervised techniques. And there is some reading material. If you want, you can go do a dig deep into the machine learning introduction at the ETH. There are also decision forests and computer vision. Units is what I'm going to talk about in the very end of this lecture. And so that is the information that you can read on to if you like. We have different methods that I'm going to talk about. For this kind of work, it's useful to use something called pipelines, which I'm going to describe. And then, of course, we have the two cases of classification and regression, and finally, segmentation. So there are a lot of different techniques. So we can use the supervised techniques on. So one is the classification problem and the regression problem, and of course you can combine them in some way. Typically for the supervised method is contrasting now to the methods I talked about before, is that you have a training session where you expose your model to data where you have the answer, and then afterwards comes the case when you really want to use it. So you have a small section of data which you train up, have your model, you're happy with it, hopefully, and then you continue with a big problem, say your large data set where you want to segment many, many images. And the important thing is that prediction is done on unseen data, so the method doesn't know about this data yet. So we start out again creating some data, and well, come back to the beloved blobs. So here we have the blobs again, and we want to do something with them. We have different groups, and we have positions in the data set. And the first one is an algorithm called nearest neighbor, or k-nearest neighbor. And it's essentially what it sounds like. You assign a class to what the class that is closest. So if we look at, for example, this one, that is kind of an ambiguous case, but it could be, it's most likely that it's the shortest distance is to this point. This one is slightly more remote. This one is pretty obvious, it's in the middle of the blob, so it's clear. And this one, well, right now it looks like it's closest to the green one, but in the case when we add more neighbors to the selection, you can see that if you would have the three nearest neighbors, then it's the question. And then it changes from that class to that class, because you have one of green class and two out of the purple class. Also here, I need to actually look at it, but I think that would turn into the yellow class, because these two here, they are closer than that one. So that would go into the yellow class in that case. So this is a very simple approach. So the training goes about just filling in a lot of data in the same, same way as we have here. We have different positions and we have group IDs. So that is the training, actually, that you fill a database of with a lot of points. You can also do it with text, for example. So let's have the training data that you have the inputs 1, 2, 3, 4, and the classes I am a dog, and let's fit it, and then we get a classifier out of it, and next step would be to do a prediction based on it. So we have here the inputs, just taking the vector that we had as the training data, so that would be very close to all the data points. So it's a given answer. So the output of this data would be I am a dog. If you, for example, would change this to a 0 here, then it would I a dog. So this is more like a direct indexing what we're doing here. But now let's try with some other values. So we have a value 1.5, which lands in between two classes. And we have the value 100, which is far beyond number 3. So given the classes we had, you have the classes, let's see, oh, that one died. Let's see if it comes up again. Yeah, there it is. So what you have is I am a dog. Oops. That's 1, 2, 3, and no, sorry. Okay, should be 0. Okay, let's keep it like this. So now I'm shifted by 1 step. But anyway, if we say 1.5, it goes, well, I should actually say 2.5 in this case now, the way I've written it. That would land in between here, and it would point to that one. The 100, which is far away here, is still closest to the dog. So it's assigned the dog. Now let's try this on the blob data. So we have a training data and produced training data with 3 different classes, and comes out like this. And now we try to fit the test points, which are X and Y, and train them towards the group ID. So now let's run this training. Was pretty quick, and then we'll go on and see what we can get out of this prediction. What I'm doing now is to create an X and Y field, so that's more or less our input data, to get the decision space out of this algorithm. So with a single neighbor, we get test points and the boundaries between the classes like this. That means these points are all closer to a single point in the purple cluster, while all these, the green ones, are closer to a point in the green cluster. So you can see here you have a little island, and that's caused by this one. So you have 2 points that are still closer to this green point, and that gives us this little island. And here in this area, there's a little bit of confusion, as you can see also in the selection here. It also gives you a little bit fuzzier transition line between the different classes. So what we can do to get it more stable, to get rid of these islands and the fuzziness in the boundary, we can increase the number of neighbors. And the result of that is now that instead, when we have 4 neighbors, that we have much nicer lines between the classes, and they actually also make more sense. And with that, we can increase the stability. probably to a certain point. It depends also on how much overlap you have between the classes, but I wouldn't say you need more than 4 or 5 neighbors and have an extremely good classification. Number of neighbors also has a point in how long time it takes. So it has to find the 4 neighbors. So it has to search through the data in order to get these points. Another one is a method of we can use is linear regression. So essentially it is linear curve fitting. So you want to fit some kind of line through points. Sometimes it also points in a multi-dimensional space. So it could be some planes or hyperplanes in that space. Method is pretty easy to understand and interpret, and usually also pretty fast to compute. Okay, the fitting phase may take a little bit longer. No, the training phase may take a little bit longer, but afterwards you just apply this polynomial function that you have defined, and that's pretty quick. So again, we need some data. Right now I'm giving you the very simple, a straight line without any jitter. So we have 4 points following some straight line through the data. And what it fits is the slope is 10 and the intercept is 10, which actually makes sense if you look at the data. Now we can try what happens when you apply the model on some of these data points. And I don't know why this takes time. Whoa, something happened. That I don't know. It worked just before. So in principle, what we would have is 2 points. One is 5010, and the other one is 990. Why this happened, I don't know right now. I'm not going to debug it, actually. And what you can also do is looking at these 2 blobs, saying that the yellow ones are blob 1 and the purple ones are blob 2, or actually 0 and 1. And then we can run the same fit again. And from that, we get some, now we run the fit. So that gives us a slope in X and Y and some offset. So that's the bias of the plane. And that we can use to, again, with these testing points. And then we can say that values above 0 are class 1, or class 0. No, sorry. Values which are greater than a line between these 2 classes, they are attributed to class 0 or class 1. And you can see that there is like as if there was line between them. You can see that the gradient has the same slope. So that is our segmentation line between these 2 classes. Another way, now we're really going away from the linear approaches, is use decision trees. And in principle, you have probably seen flow charts already, and trees is very commonly used structure in data science, where you more or less have a node and vertices going out in different directions, and blob like that, and so on. So it's a very popular structure. It's quick to search in because you have the longest search path in such a tree is the height or the depth of the tree, and that makes it quick to find the answers you are asking for. So let's look at the decision tree. We have here different data points. We have 1, 0, 1, 2, 3, which are located in the classes 0, 1, 0, 1. And from that, we train the tree, and that gives us a tree looking like this. May look a bit strange to begin with, but let's look at what we do. Let's look at if the value is less or equal to a half, then it should go in this direction. And then we have one sample in the class, and in one sample in this leaf, and we have one value assigned to the 0 and 0 values assigned to the 1. If it's false, then we go in here and check. If it's less than or equal to 1.5, we have 3 samples, and one sample is in class 0 and one sample is in class 2. And then we go in here, and then we have the true again on this side. We have 1 for the ones and 0 in the zeros. And then we go in here. So you split down, you make decisions in every case, and you have a threshold on every level. And then after a while, you can go through. So if you would have a 3 going in here, it's greater. It's greater than 0.5. So that's false. A 3 is still greater than 1.5. Going here, still greater than 2.5. So we assign it to class 1. Is that a question? No? So let's go on. On using it on this data. We have again the blobs. Can someone mute the microphone, please? We have the blob data again and see what happens. And that was a training. And let's go to the next slide. And we start out, we have relatively uniform distribution among the classes. And now we have different threshold values. And you can see here that in the end, in the leaves, we have class equal to 1, class equal to 3, class equal to 2 and 3. So these are the leaves in this segmentation, and the resulting testing points give us this banded shape there, where you have one band for the yellow ones, one band for the green ones, and one band for the purple ones. Not really a smart segmentation as it is right now, so it's maybe not the best choice to have this kind of tree for that data. So we need to go do something else instead. And that something else is to use random forests. So we know trees, and trees, a forest is many trees. So what we have is we have different trees, like this one, which gives one thing, and then from another fraction of the data, you have a tree that looks like this, and then you have yet another tree, maybe looking like this. And what you do is running all these trees and saying that this says it's class 1, this says it's class 2, and this says it's class 1. Then you take majority voting out of the trees, so the whole forest says this data point is class 1. So the important thing is that you split the data into separate points, separate subsets, and each subtree in the forest gets each one of these data sets, and then running it through. So let's look at a little bit more complex clustering. Here we have blobs that are much closer together and they're overlapping a lot. And that's not so good. So let's build a tree random forest classifier. And in this case, we choose to do 5 decision trees. So there are 5 voters in this classifier. No. Oops. Hey, that's why. So, and looking at the trees, so we have now 5 different trees. So let's look at the 0. And this is a huge tree, actually. You can see here that there are many different branches until you end up in the different leaves. And the reason why the tree is so complicated is that the data was overlapping and there is a lot of ambiguous cases, and that gives you a large tree as well. And looking at the next one, it's same thing here. It's also maybe not so large. Yeah, well, it's also pretty big. So then you get 5 such trees, and they are all applied to the data point that you provided. And the result of that is we have training data, the simple training data again. And the first decision tree gives you this one, the second decision tree gives you this one. You can see that they are not completely the same. And then we have another 3 different trees, and the effect of all 3 of them starts looking like something that the k-nearest neighbor with more neighbors in it. The problem is also you can get very detailed, so you kind of overfit when you run these trees. Now, as you already have seen, many of these image processing tasks, they are quite sequential. You apply a filter, then you apply some modification of this kind, and you apply a threshold possibly, and then you do some morphological operation. And this kind of work can be formalized in something called pipelines, which is provided in the Python packages. So again, let's get our beloved blobs. And now we create a very simple pipeline where we just have the robust scaler. It's a rescaling module that is added to the pipeline. So what it does is essentially it computes the media value of the data, and then it normalizes around that point, I think using the standard deviation. So that is more insensitive to outliers in the data. So what you do is you define the pipeline, run it, and then you can see what happens inside the pipeline. So we have the input data, which looks like this. Then we normalize it. As you can see here that the values are between 10 and -10. Normalization, then it goes more like between ±1. Also the histograms, you can see that they have changed positions a little bit. And that is the principle now, that we want to run several steps and they do different things to get the data to the point we want it. Now another one is we're adding something called a quantile transformer. I don't remember exactly what that was doing. It's dividing it in also again some kind of normalizing the data within the ±0 and 1. Then comes the robust scalar, which places between plus and -1. And then you can see here how the data is changing with the different operations. Then you can also add something like polynomial features. that's actually expanding the feature vector. So what you do is, in addition to the data itself, you will also have, in this case, polynomial features up to second order polynomial. So we'll get the x, y, and multiplication and the x squared on top of it. So you expand the data pretty much here. So from 2 dimensions, 3 data channels, you get 9 data channels in this case. And that's also a thing you usually do when you start creating features, is to try finding higher order polynomial components that may provide relevant information into the feature vector. Some of them are useless, other ones are really the big thing. So then you have to explore which ones are really useful. So one important, right now we have, until now we have only said that this point is equal to something, and that point is equal to some other class. We have been talking about points, and the next step is to talk about classification. So putting an entire image into a category. So that could be dogs and cats, or cars and boats, or buses, and things like that. And a typical problem, which is used a lot in the classification, is to classify in digits between 0 and 9. So we have the MNIST dataset, which you heard about some weeks ago. And let's load some images. We have images of the numbers 0 to 9. They're not very big. And so they are 8 by 8 pixels, and they have 4 bits. From that, we have 50 samples. So that gives us this data set, which you can see here, down here, image data, 50, and that's the image size. So now we want to run some kind of pre-processing pipeline on that. And let's see what comes out. We have the numbers, and they are flattened into different gray levels. So we have 16 gray levels, as we had 4 bits. And each image, or this is the representation for among the images. So how many pixels you have on each image with this value. Then we normalize it, bring it together, because the machine learning methods, they prefer if the data is more compact. And then you can see, well, we can't. The histograms would be down here, so you can maybe scroll it down. Right now it doesn't want me to. But the histograms would be on the lower part of this one, but we get so many labels here. So now we want to do a classifier on a k-nearest neighbor classifier in the pipeline with k equal 1. So we had a flatten, normalize, and now we take the nearest neighbor and see what happens. Now I really need to go out of this. So, and here you can see that we have all the, let's see, the nearest neighbor gives a color to each of these dots, and the color corresponds to the number. As you can see here, the red dots correspond to the 0. So you can see a red dot down here. So those are the zeros, and so on. So this is what the classifier provides. And let's go back to the view. So now we want to test the classifier performance. So let's test it with the training data. And let's run that. And we see, yay, we got 100% accuracy. That sounds good, right? How about the confusion matrix? How good are we on that one? Fantastic. We can see that we get 7 zeros, 5 ones, and so on. So and no misclassifications. So this sounds fantastic, doesn't it? Let's look at the report of it, and we can see also different precision recall. This would be the dream of having a classification method, having something like this. But you probably can already hear that something is not really correct. Even though we think, yay, we got the fantastic algorithm and let's make a patent and call Google and sell it for much money. It's not like that, actually. So let's try again. Let's try it on unseen data. So what we are looking at now is an image of something called, should resemble a 9, even though it's a very sloppy 9, I would say. And the prediction came out as 7. So now we start seeing that something is not really right. And that is the problem. We did the training and validation on the same data, and that's not allowed. And in some cases, calling the training crime in machine learning. What you need to do is, if you have a data set, you have to split it into 3 different parts. And one part is, of course, the training, which is important. Then you have the validation, that's the feedback data while training to see how well you progress in the validation. And then finally, when you want to check the performance of your method, you need also the test data. So this is what you need to work with. And don't forget it, because you can get very misleading results if you don't split the data in these 3 categories. So with regression is another option. So we talked about classification before. Regression is putting values, so getting actually analog values out of the category. So the classification give you a category, so it's a clear 1, 2, 3 or whatever. With regression, you get the actual decimal number, or plus minus a little bit. So you make a fit to the classes instead, based on the image content. And that we need just to load some images and go on. And let's do a regression check, and then we have the data 1, 2, 3, and so on. And then you can see here that the regression, nearest neighbor regression, gave us actually the values here for image 1. The first image gets a 0, the second image gets a 1, and so on. And it makes pretty much sense. And also you can see that the last 2 are zeros, and this is a 1. So actually the regressor gives you the number directly out. Also, we need to assess it somehow to see how well we perform. And as I got the question some weeks ago, the ROC can only tell between binary data, so if true or false, and that's the thing. So what we need to do is to have some other metrics to work with. Typically used are mean squared error, which you know from, I believe, any statistics class is practical, or mean absolute error, which is kind of similar, but a little bit different value. So let's try doing some training again and see what comes out. And now we can see when you do the predictions based on the training data, you have a very nice fitting. The average error is 0, so all these dots, they land on exactly the right value. The dots, they are just a little bit distributed. You can see how many they are. It's not telling about the real value. It's just a jitter added for the visualization. If you then start doing it on the validation data, you start seeing that, okay, the main diagonal is doing pretty well, but in some cases you get misclassifications. So for example, the 1 gets misclassifications almost over all other numbers. And also the 9 gets pretty many misclassifications and so on. So you can start seeing in this matrix. So it's like a confusion matrix, what we get here. So what happens now when we increase the neighbor count? So we set the regressor to work with a 2 instead. Oops, no, that wasn't meant to be. So, and then we start getting a little bit in trouble, because you can see here there are some misclassifications in the data all over the. Some are well classified, other ones are not so well. So you get some uncertainty if you start putting in a second neighbor. And now I need to switch here, because otherwise we won't see it. And with this one, we have, you can also see, if you compare this validation result with this one, you can see that it's making a lot more errors than before. Also, when you try it on the training data, it starts getting confused, even because the second neighbor starts voting in. So the last part, I think I'm going to do a little bit overtime. Hope you don't mind. So the last part is that we want to do pixel classification. Now I stay in the notebook view, because there's a lot of things happening all the time, and the output will anyway exceed the screen. So what we have done is single class, yes. I get the question how the size of the training data set affect the prediction outcome. It certainly does. It's easier. So if you have a very sparse, also few data points to compare with, the risk of doing a misclassification is much greater. So if you have a big blob with many data points, it's much easier to find the right value, because it's easy to get closer to the specific one in the data. So, of course, in general, when you do machine learning, large data sets are always appreciated to avoid to do too many errors. On the other hand, too large data set has the disadvantage of it takes a long time to train. And in some cases, we can talk about days and weeks for the training. So that is something you have to balance, how well you want to train your data set and how long time you can do it. But in general, more data points is good. So before we wanted to put classes on whole images, and now we want to look into more single pixels and what we want to assign for value on those. And that is the segmentation problem. And the example I'm going to work on now is segmentation of this image of mitochondria. And the data is in a way that human eye can spot them pretty easily if you know what you're looking for. But the problem is many structures have the same gray level distribution, and also signal to noise ratio is maybe not ideal. So putting a single threshold on this, which we did last week, I think, doesn't help much. It gives you a lot of misclassifications. Also, filtering wouldn't help, because the filtering is not smart enough to extract the structures we want to look for. So now we are going to try all the techniques I have talked about for the last hour. So we're going to look for decision trees, random forest, linear regression, nearest neighborhood, and that in combination with different informations. So trying to play with the data and see what comes out. So first, let's load the data. So we need data for training and validation. And in this case, as we only have one single image, we want to split it into two pieces. And that is what we're going to do in the next cell. So here I'm taking for the validation image, I'm taking the training image, I'm taking the first 256 columns. And for the validation, I take the remaining 256. And then our data looks like this. So we have a training image and training mask, validation image and validation mask. And now the mask tells which are the regions we want to identify. So let's first start with a regression tree and see what comes out, do some fitting, and now we have got a huge tree. As you can see, it's pretty big. So let's see what happens. Here we see the pipeline and what the steps are doing with it. And now let's see what the performance is when we try to use it. So the training image gives this. And the training mask, which was what we gave it, was this. And then the prediction mask turns out like this. So this is what we predicted. If we take the full image and compare that, we can see the full image, and then we see what the trained data looks like and what's the predicted data on validation data. So that's a way to see before seen and unseen data. So that didn't work pretty well. So you see that there's a lot of misclassifications. So that one wasn't what we needed. So let's go on and see what happens then. Train a new tree, but this time we add X and Y positions in the tree. And of course the tree is getting big again. And now we can see that the feature information is the image, X and Y information. Then the different steps do flattening, normalization, and creates decision tree. And now we can see if it did some improvement to the data. There was some improvement, but not really what we wanted, and in particular, so it starts identifying regions that are relevant, which is good. But if we look at validation data, you can see that, well, not very good. It's more or less just stretching this information that you have out here, stretching it out, and as there were no other pieces here that connect to the wall, nothing else comes into the validation data. So that is not very good, a good tree to do the segmentation. So let's continue. Now we try a combination with k-means and random forest regression. So we make it a little bit more complicated. So k-means produces already 4 classes. So it reduces the complexity of the data in addition to X and Y positions and the image data itself. That also takes a little bit. My poor computer here at home is not that well performing today, so it takes a little time to train it. And then you can see here what the k-means was doing, some kind of interesting classes here. And the random forest did something. And now let's look at what is the output. Yeah, it starts looking at least like if we try it directly on the prediction mask, that the mitochondria are starting to come out as they should. But if we look at the validation mask, the performance is not so convincing anymore. So still not the thing that we wanted. So let's go on adding some other features. So in the next one, we add polynomial features instead of the k-means. Let's see what that gives. That also takes a little time, of course. And what will be the output of that is the question. So now you can see what the polynomial features look like. The output is pretty fantastic for tests on the training data. But looking at the prediction of that, it's still not doing pretty well. It starts getting at least the parts that are connected to the border, but not the rest. So it still didn't get. So we need to add some smarter features than we had before. Now we're going to use the difference of Gaussian filter again. And the filters we are using is, first of all, the normal Gaussian. And we're going to use this kind of edge detection filter and this kind. So there are two different bandpass filters that we are working with here. And now we run this. So all these filter steps are included in what we call filter step here. So that's a function in a Python function, Python file outside of the notebook, which is imported here. And now we can see what happens with that. And first of all, the features are the image, a smooth version of the image, sharp edges and blurry edges. So we have some more spatial information compared to before. And that gives us now a different result. So this one did pretty good on the prediction mask, even though there are some problems around here. But also in the validation data, it starts getting the right thing. So now let's try something else using the neighborhood, which is actually moving the image around ±1 pixel in different directions. And then I need to run this one and start the pipeline. Now only using the neighbors. So what we get is the image itself plus its 8 neighbors in all directions. And that is what you see here. And each neighbor here is shifted by 1 pixel in X and Y, depending on the position here in the matrix. And that will give us some results. Maybe not so convincing again. We come back more or less to what the first predictor was doing. But interesting thing is that this actually is, this moving around is the same as a convolution, because that would be the convolution with just a box filter. So that we could use instead. But it has some relation to that, but the output shows the effect of a convolution, so maybe not really what we wanted. Oh, I need to run this first. So here you get the weights for the convolution, and then we can run the very same convolution here and get the same prediction. Now we combine again these neighbors with the nearest neighbor classifier. No, run it. And see what happens. We have some interesting classes here. See what comes out of that. This takes a little time, apparently. Yeah, there we go. yeah, it did a very good prediction on the training data, but if we go looking at the validation data, it's not so convincing. It does actually predict point clouds around the places where you should expect some features, but still not really good. So now we have tried a lot of different techniques on clustering and trees, and no one of them were really able to handle it. So the next approach is to go for the big machine, and that is going into neural networks and machine learning, the big thing in machine learning. And in particular for image processing, what is used is the so-called UNet, and the construct of that is in principle that you have the shape of the architecture of this network is looking like a U. And what you see, the elements here are different filter steps doing convolution, so it's a convolutional network. And what you see here is a downsampling, so it's doing downsampling and again lot of convolution and downsampling and so on. So it goes down to a certain point and then again going up to upsampling into the final image size, and then some of the information is also propagated across on each level. So it's a combination, and with that combination you can get different scales in the image, in the classification, and that helps a lot. So what we are doing now is to build a network based on a certain amount of convolutions. So in each level we have 2 convolutions, then we do a downsampling, convolution, downsampling, convolution, and then we do upsampling, combining different layers. So with this code here, you are building the whole network, including a lot of convolutions, etc. So if we run this, you get some structure driven and drawn up like this. So it's a pretty big network now. No, for the screen it's pretty big, but in other applications it may not be so big. And then you can also see what the different steps are doing as a summary of the report of the network. So now we need new training data. Neural networks are very time consuming, so we need to be a little bit modest, at least for the computers we have available right now. For larger problems, you can take a larger computer, you can go to clusters, you can use graphic cards to speed up the computation. But right now, for this purpose, we just go for a small data set. So let's find the data. We have a training image, which is smaller than the validation image. Running the prediction is much cheaper than running the training, so we can afford to have a larger validation image. So let's just run the classification or the segmentation on untrained models. So all the filter settings in the network, they are set on default values, and let's just see what comes. Then what we get is the training image, the training mask, the full image, and then we see here the predicted segmentation, and it looks pretty much similar to what we did when we did convolution before. So it's not really helping us a lot, but it's natural. If you just run something based on a lot of convolutions stacked on each other, this is what you would get. But what we do right now is a demonstration. So we use the same training model, same data for training and validation, more or less. So we don't give a big variation in the tests. The loss function may not be the best one. We're going to use the mean absolute error And let's see what comes out of this training. But it is not the best choice, but for what the time we have here now, we have to settle with that. So what I'm doing now is I'm starting a training based on 20 epochs, and one epoch is a training iteration. And what we do is now we have this mean absolute error that is computed, and you can see here how the mean absolute error is changing during the training steps. So we had a large error to begin with, and now they did a big jump to start, and now there are fine tunings. Also, the binary accuracy, which we measure, is in the first round, it's very bad. So we don't hit very many of the right ones, of the right values in the mask. But then pretty soon you come up to 91% binary accuracy. What else is there to say while we are waiting for it to happen? The loss function is kind of a cost function that is used in the optimization, and also that one should decrease with the epochs. If it doesn't decrease, then something is wrong. And now we got the last one. Good. And there it is. Good. So now we can look at the result. You can first look at the mean absolute error, which I already tried to sketch out here. There was a large error in the initial step, but then it slowly asymptotically goes towards a small value. That was for the training data, and then for the validation data, it's actually better. Then we go for the classification accuracy. In the beginning, it's bad. And then after a while, we come up to something like 90% accuracy in the classification. Now, what does it look like? Let's look at the images when we apply these. So we have the training image, and this is the predicted output. So the output is not classified values, but it's more probability that it belongs to the class. And here you can see that there's a large probability that you have something here, which is true. Also here and here. Here is something that is confusing. And then you get something here and here. And this piece here is also pretty good. Looking at the overall performance on the whole image, you can see that it's actually doing, I would say, the best result what we have seen until now. So this is good. A problem when you do the training is that you can also do overfitting. That is training it, so it does a fantastic job on the training data. But if you go just outside, it's not generalized enough to see what its performance is, or it's not generalized enough to find the same features in other data. So if it's the dice coefficient, I'm not sure actually. I have to check that. I don't think so. It's probably just hit and miss, and the dice is a little bit more than just hit and miss. So I'm not sure if it's really the same. I have to check that. But it's related to the dice score. Where was I? Yeah, overfitting. Yeah, so the consequence is when you have overfitting, the performance is going down if you don't provide exactly the same thing that was done on the training, which is something you don't want to. Let's try another one. In this case, we only do 5 epochs. just to shorten the time a little bit. Here you can see actually the binary accuracy is going down, and also the error is increasing at some point. So we are doing this effect here. But let's see what comes out of that one. Yeah, then you get really confusing curves when you do this overfitting effect. Finally, we can see what comes out of that one. Yeah, this is what it resulted in. So not really reliable data. So that is the cost when you do the overfitting. So I did some overtime today, but maybe we can compensate it with that there is no exercise session today, but instead we do it by mutual appointments by email. If you have some problems, please email the results, your questions before, then I can also prepare and be more efficient in answering your questions. The last part here now is just a little bit summary. So we have went through the concepts of supervised segmentation, different classifiers, also looking at the difference between classification and segmentation, where we used also nearest neighbor technique, trees, random forest. Regression versus classification, we saw that the regression provides actually values on the way, and classification showed the assigned class to the trained data. Important is to split the data into training, validation, and test data to avoid doing mistakes in the evaluation and quality assurance of the model that you have trained. And finally, I showed you an example of how deep learning can work with this mitochondria data. And well, that was it for today. I'm still working on the solutions. They will come. I would say I would probably do it as the next step after this lecture. So thank you all for coming, even though we are remote and not seeing each other in the same way as usually. And stay healthy. See you next week. Thank you.